Hey everyone! Today we're going to tackle a classic physics problem. Seriously, it's one of those challenges that seems pretty simple on the surface. Just a guy on a raft, but it beautifully unpacks a huge concept in mechanics. By the time we're done here, you're going to have a powerful new tool in your problem-solving kit. Now, this problem, it comes from a pretty legendary book, Problems in General Physics by Irodov. And if you've spent any time studying physics, you know this name. This book is famous, or maybe infamous, for problems that really make you think. They don't just test if you can plug numbers into a formula. They test if you actually understand the physics. So here's the setup. You've got a raft and a man on it. Both are totally still. Then, the man decides to take a walk, moving a certain distance along the raft, and then he stops. The problem asks us two things. First, how far did the raft itself slide across the water? And second, what was the force the guy exerted on the raft to make it all happen? Okay, so faced with a problem like this, where do you even start? Before you even think about writing down F equals ma or anything like that, the first job is to play detective. We need to find the core physical principle, the one golden rule that's going to unlock this whole thing. So look back at that text. Read it again. There's one little phrase in there, just a few words, that's the absolute key to everything. You might even glance right over it if you're not careful. Do you see it? And there it is. Assuming the water resistance to be negligible. This is so much more than just a way to make the math easier. This is the big clue. This tells us that, in the horizontal direction, there are absolutely no external forces messing with our man and raft. And that phrase, no net external force, that should set off a giant light bulb in your brain, because that is the one and only condition you need for one of the most powerful laws in all of physics, the law of conservation of linear momentum. It means that the total amount of motion, the total momentum of our system, whatever it is now, it has to stay that way forever. It cannot change. And that's really the whole ballgame. Our man and raft together are what we call an isolated system. There's no engine pushing them, no wind blowing, no current dragging them. So their total momentum is stuck. Now compare that to, say, a speedboat. The motor is an external force. It pushes on the water, and the water pushes back, and the whole system accelerates. Its momentum changes. Our raft can't do that. All right, so now that we've found our golden rule, conservation of momentum, we are locked and loaded. We're ready to tackle the first question. Just how far did that raft actually move? So the trick here is defining what our system is. It's not just the man, it's not just the raft, it's the man plus the raft together. Now think about it. What was the total momentum of this system at the very beginning? Well, they were motionless, so it was zero. And since momentum is conserved, that means the total momentum must always be zero. And here's the big leap. If a system's total momentum is zero, its center of mass is not moving. It's like it's anchored to a fixed spot on the lake. So with that one powerful idea, our plan becomes super simple. It's basically a 5-step recipe. We're going to define our starting line, write down the center of mass position before and after, set them equal to each other, and then just solve for what we're looking for. It's all built on that one idea: the center of mass does not move. Okay, let's put some math to it. We'll set our 0 point on the shore. Initially, the center of mass is at 0. Easy enough? Now for the final state. This is the tricky part. Let's say the man walks a distance L prime forward on the raft. But while he's doing that, the raft itself slides backwards a distance L. So, relative to the shore, the man is now at position L prime minus L, and the raft center is at position negative L. We plug that into our center of mass formula, and the whole thing still has to equal 0 because it hasn't moved. And when you do a tiny bit of algebra, out pops this beautiful, simple answer. The distance the raft moves, L, is just the man's mass divided by the total mass times the distance he walked. And this just makes so much physical sense, doesn't it? I mean, if the raft is gigantic, if M is huge, then the raft barely moves at all. If the man is really heavy, the raft moves more. It moves in the opposite direction, which is exactly what you'd expect. It all checks out. Okay, awesome. We've got the displacement figured out. Now, let's move on to part B, finding that force. And this is where a really common conceptual mistake can trip people up. So let's walk through it nice and slow. And right here is the trap. You might be thinking, hold on a second. You've been telling me this whole time that momentum is conserved, which means the net force is 0. So how are we suddenly solving for a force? What gives? It's a great question. The answer lies in knowing the difference between external and internal forces. The net external force on our whole man and raft system is zero. We know that. But that doesn't mean there aren't forces acting inside the system. The force of the man's feet pushing on the raft, that's an internal force, and it is definitely not zero.
And what do we know about these internal forces? Well, they always follow Newton's third law. They come in pairs. The force the man pushes on the raft with is perfectly, exactly equal and opposite to the force the raft pushes back on the man with. They're a matched set. And if you look at the system as a whole, they perfectly cancel each other out, which is why they can't change the system's total momentum.
So if we want to find that force, we have to change our perspective. We have to stop looking at the whole system and just zoom in on one piece of it. Let's look at the raft, and only the raft. From the raft's point of view, what horizontal forces does it feel? Well, just one, the man's feet pushing on it. So we can just use Newton's second law for the raft by itself. That force equals the raft's mass times its acceleration.
And after you crank through the math, this is what you get. Now look closely at this equation. The force isn't just a number. It depends on dv bar dt. What's that? That's the man's acceleration relative to the raft, which makes total sense. You only exert a force when you're speeding up to start walking or slowing down to stop. If you're just cruising at a constant velocity, there's no force. That little mass term out front, by the way, is a cool thing physicists call the reduced mass of the system.
So what's the big picture here? We didn't just solve one random problem. The method we just used, the whole thought process, is a powerful toolkit that you can use on tons of problems, involving explosions, collisions, or anything in an isolated system. So here are the key steps to add to your physics toolkit. Number 1, always define your system. What's inside, what's outside. Number 2, hunt for those magic words like negligible friction. That is your signal that momentum is conserved. 3, remember your secret weapon. If momentum is conserved and you start from rest, the center of mass is your anchor. It's not going anywhere. And finally, 4, understand the difference between internal and external forces. It's absolutely crucial. So I'll leave you with a little challenge to try out these new tools. Let's change the problem. What if instead of walking and stopping, the man just jumps off the back of the raft with a known velocity u? Can you use these exact same principles, conservation of momentum, to figure out how fast the raft would be moving in the other direction? Give it a shot. Thanks for joining me on this one.